Welcome students, welcome to TKG Physics classes. Today we will talking about an important part, that is equipotential surface and its properties. Okay, in chapter 1 we learn electric field lines and the properties of electric field lines. In chapter 2, that is electric potential and capacitance, we will learn equipotential surface and its properties. So first of all, what is equipotential surface? You just see the name equi, that means equal potential at a surface, that means any surface which have same potential, same electric potential at every point on it is called equipotential surface. Equipotential surface. You know, if there is a charge plus Q and you have to calculate electric field at point P as well as electric potential at point P, you know the formula, that is V is equal to 1 by 4 pi epsilon naught amount of charge divided by this separation. Suppose this separation is R. Now if I make a sphere here, this is the radius, so this distance is also R, this is also R, this is R, this is R. Now if I calculate electric potential here, what will be the expression? The expression will be the same, that is 1 by 4 pi epsilon naught charge, that is Q, and this separation is also R. So at this point and at that point electric potential same. Similarly at that point also electric potential same, at that point electric potential also same, similarly at that point also same. So this surface, this sphere is called equipotential surface. Clear? Now if we calculate electric potential at point P dash, what will be the formula? Suppose this separation is R dash, and the formula will be V is equal to 1 by 4 pi epsilon naught Q by R dash. Now draw a sphere here. If this separation is R dash, then this separation is also R dash. Clear? This separation is also R dash, this separation is also R dash. So at that point, electric potential formula is same, so the value of electric potential will be equal. So this surface, this sphere is also called equipotential surface for charge plus Q. So here for point charge, the concentric spheres is called the equipotential surface. Now for a linear charge, what will be the equipotential surface? If we consider a linear charge, that is, you consider plus linear charge. Now you just calculate electric field or electric potential here. What you have to done? If I draw a cylindrical shape, at this point potential same, at this point potential same, because this separation is same. Here also separation is same. So this cylindrical shape, this cylindrical surface is called the equipotential surface for linear charge distribution, line charge distribution. Clear? This surface also be this cylindrical shape this cylindrical shape also be the equipotential surface for, that is, for line charge distribution, so for linear charge, the concentric cylinder is called the equipotential surface. Clear? Now we have to learn some properties of equipotential surface. First properties. Properties number 1, that is the definition. Equipotential surface. That means at equipotential surface, the potential difference will be 0. Question is why? If we consider this surface is an equipotential surface, and we consider 2 points here, A point and here point B. Point A and point B both are lies in the equipotential surface, and we know the definition, that is equal potential. At that surface, every point the potential value is same. So what will be the potential difference? If we take a charge Q0 from A to B, then the potential difference formula will be final value, that is VB minus VA, and VB, that is V, and VA, that is also V. So the potential difference is 0. So first property, that is at equipotential surface the potential difference is 0, because at equipotential surface for every point the potential, electric potential value is equal, same. Now second properties number 2. No work is done in moving a test charge over an equipotential surface. That is, over an equipotential surface, let's consider this surface is an equipotential surface, and we are taking a charge Q0 which is moving from point A to B. So what will be the formula of work done? You know the formula, work done, that is equal to charge Q0 into the potential difference between 2 points, and here final point is B, initial point A, so the potential difference is VB minus VA, and you know the potential difference over an equipotential surface, that is 0. So Q0 into 0, that is W is equal to 0. Clear? So this is the second point, and an important point. Okay, no work is done in moving a test charge over an equipotential surface. Now point number 3. Point number 3 is also an important point, that is electric field. Point number 3. Electric field always normal to the equipotential surface. Electric field is always normal to the equipotential surface. That means if we consider this is an equipotential surface, the direction of electric field will be normal. Question is why? Okay, if the direction of electric field is not normal, that is, suppose say the direction of electric field is around that side. So this E has 2 components. This component, that is E cos theta, taken this angle theta, and this perpendicular component is called E sin theta. Now E cos theta component, this is a non-zero component. And you consider here is a test charge Q0. For moving a test charge q naught against E cos theta, what we have to done? We have to done work done for taking test charge along that side. We have to done work done because along that side there is a non-zero component of electric field. But you know there is no work done. No work is done in moving a test charge from one point to another point over an equipotential surface. There is another reason. You know the potential difference formula dV, that is equal to minus r1 vector to r2 vector E vector dot dr vector. And over an equipotential surface, what is the value of dV? dV represents the potential difference. So value of dV, that is 0, that is minus r1 to r2 E dot dr is equal to 0. There is a dot product of electric field and distance, 0. And you know the dot product, that is E dr cos theta is equal to 0. What is theta? Theta is the angle between electric field and the displacement, or you may call it distance. So from here, E cannot be 0, dr cannot be 0, so cos theta will be 0. That means cos theta is equal to cos 90, that is theta is equal to 90 degree. And theta is equal to 90 degree, that means suppose this is the displacement dr, you are moving a test charge from along that side here, and this is the direction of electric field, and this angle theta is 90 degree. So you can say this electric field is directed always normal to the equipotential surface. This is point number 3. There is another point, that is point number 4. Okay, and the point number 4 is no two equipotential surface, no two equipotential surface can never cross each other, can never cross each other. Why? You just consider, suppose this is an equipotential surface, this is another equipotential surface, and you know the direction of electric field over an equipotential surface, that is the direction of electric field is always normal over an equipotential surface. Suppose I consider this is an equipotential surface, this is an equipotential surface. So for this equipotential surface, what will be the direction of electric field? Along that side, normal, or maybe that side. Clear? So this is an equipotential surface which is vertically. This is an equipotential. What will be the direction for this equipotential surface? Along that side. We consider. And if I consider this is an equipotential surface which is placed horizontally, what will be the direction of it? The direction of it will be along that side, or it may be along that side. So for this case, for this equipotential surface, you consider this is 2, this equipotential surface 1. For equipotential surface 2, the direction of electric field will be along that side. So if two equipotential surfaces cross each other, what will happen? Here two equipotential surfaces cross each other. When they cross each other at a point, there will be two direction of electric field, and you know at a particular point the two direction of electric field is never possible. So we can say that no two equipotential surface can never cross each other. Clear? So this is point number 4. There is another point, that is point number 5. And in previous class we discussed the topic, that is the relation among electric field between electric field and electric potential, that is E equal to minus dV by dr. From here you can say for same change of dV, for same change of dV, that is E proportional to minus 1 by dr. That means electric field inversely proportional to distance. Clear? Which indicates if there is a strong electric field, that means the equipotential surface far apart, that is equipotential surface far apart. And if there is a weak electric field, equipotential surfaces are closer together. So this is all about the properties of equipotential surface. So first properties, that is equipotential surface. In equipotential surface the potential difference, that is 0. Second properties, that is no work is done in moving a test charge over an equipotential surface. Third properties, that is the electric field is always normal over the equipotential surface. Fourth properties, that is what we learn. Fourth properties, that is no two equipotential surface can never cross each other. And fifth properties, that is for strong electric field the equipotential surface closer together, far apart, and for weak electric field the equipotential surface closer together. Now you have to learn draw diagram, that is suppose there is a unit positive charge and you have to draw equipotential surface for it. What will be the equipotential surface? At first you draw for unit positive charge plus Q electric field line, and you know for positive charge electric field line is directed outward. Clear? So this is the direction of electric field line for positive charge. And what is the equipotential surface here? This is the equipotential surface. You can say this is the equipotential surface. This is also an equipotential surface. Clear? This equipotential surface, which is closer to the charge, has higher equipotential because along the direction of electric field the potential which is decrease in order. So this equipotential surface has higher potential with respect to second equipotential surface. Second equipotential surface has higher potential with respect to third equipotential surface. So this is the diagram for equipotential surface for a positive point charge. Now suppose there is a uniform electric field and you have to draw equipotential surface for it, and you know the uniform electric field, that means the electric field which is directed along the same direction, and the spacing for both for electric field, that is equal. This is an uniform electric field, and in this case equipotential surface will be plane. Any place corresponding plane will be the equipotential surface. You may consider here also equipotential is a plane. This plane has a higher potential with respect to this one, and this plane has a lowest potential. Clear? Because electric field directed along x-axis. Along the direction of electric field the equipotential surface decreases. And there is another part, another diagram, that is there is a positive and negative charge, and for positive and negative charge you have to draw an equipotential surface. There is a positive charge and there is a negative charge, and for positive negative charge you have to draw equipotential surface. You know from positive charge the field line outward, for negative charge field line inward. So this is direction same. For negative charge field line inward, for positive charge field line outward, inward, and in this case outward. Outward, here outward, here outward, outward, in this case inward, 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 inward. Okay, so this is electric field line. Now you have to draw equipotential surface. There is a positive charge, there is a negative charge. So there is an attraction, and this attraction is stronger in between them. So electric field line will be, equipotential surface be like you just see this equipotential surface separation is closer because there is a strong field, and here there is a weak field. So this equipotential surface separation, that is far apart. Here also same. So this is the equipotential surface for a dipole. That is, there is positive and negative charge. So what we learn in this class? At first we learn equipotential surface definition, then equipotential surface properties, then we learn the diagram, that is equipotential surface diagram for positive point charge, for uniform electric field, for a dipole. Clear? So this is all about today class. Stay tuned and thank you.